Hello. Question 6 on the midterm asks us several sub-questions based upon a function between two vector spaces. The first question is pretty simple. It's just the definition of what is a linear transformation, or the definition of a linear transformation. Since we already know that we're dealing with a function, we just have to list out a couple of properties of that function. First, if you give me any two vectors in my domain, then I know that L will break up over addition of those vectors. And also, if you give me some scalar and a vector in my domain, then I can pull out that scalar from my function. And those are the only two things we need to have a linear transformation. The next question asks us to show that a particular function between a couple of particular vector spaces is in fact not a linear transformation. Now, to do this, all we have to do is come up with a specific example of A and V, or a specific example of V1 and V2, for which these equalities do not hold. So I'm going to go ahead and let A equal 2, and let's go ahead and let the vector, since we're inside of R2 here, I'm going to let x1 or x comma y, I'm going to let this equal 1 comma 1. And now we can do a couple calculations. Let's first calculate, using number 2 here, let's calculate L of AV. So L of A times our vector xy, x comma y. Okay. This is going to equal L of, well, we're doing 2 times the vector xy. So since A is 2 and the xy is 1, 1, so 2 times 1, 1 is going to give us 2, 2, 2 comma 2. And now by our formula up here, this is going to be 2 plus 2 times 2, which is, this guy's going to be 4, and so we're going to get 6. And now we can go ahead and do the right-hand side over here, and we get that A times L of xy, this is going to give us 2 times L of 1 comma 1. Now, L of 1 comma 1, that's going to be 1 plus 1 times 1, which is just 1. So we're going to get 2 over here, and then we're going to do times 2. So we're going to get 2 times 2, which is going to be 4. Okay? So we get that this guy on the left is not equal to this guy on the left. So we have that the function is not a linear transformation. So let's go ahead and write that down. We say that L of A of x comma y is not equal to A times L of xy. So L is not a linear transformation. And that's our question, our answer to part B. So the next question is giving us a particular linear transformation, but it's only giving us a limited information about that linear transformation. It's asking us to calculate some other point. Now, since it gave us what L of 1, 0 is and what L of 0, 1 is, and these guys form the standard basis for R2, which is the domain of our linear transformation, then we can go ahead and quick write out the matrix associated to that linear transformation. So we can say the matrix associated to L is A, which equals L of 1, 0, L of 0, 1, which in our case is just 3, 5. 3, 5. All right, so we also know that how to calculate any point of the linear transformation given its matrix. We get that L of minus 2, 3 is the same thing as multiplying by this matrix. 3, 5 times my vector, which if we do the arithmetic, we get this is minus 6 plus 15, which should be about 9. Okay. And you could put little brackets around this if you wanted, but it's fine like this too. So that gives us the answer to part C. Next question is awfully similar to that one, but they don't give us the information on just a standard basis. What we have is we have a linear transformation. We know this guy's a linear transformation, but it's going between R3 and the set of 2 by 2 matrices. Now we've said that E1, E2, and E3, this is the standard basis for R3. And what we've done is we've provided the information for L on E1, on E2, and also this random vector here, 2, minus 1, 1. And what we want you to do is calculate L of E3. So how do we do this? Well, we can't just write down the matrix associated to L because we don't have L on that third standard basis. But what we can do is we can notice that if we take 2 times E1, if we take 2 times E1 and we subtract off E2 and then we add E3, what we get is this random vector. If we then apply L to both sides and use the fact that L is a linear transformation, we get that 2 times L of E1 minus L of E2 plus L of E3 is equal to L of 2 minus 1, 1. Okay? And we know what L of E1 is, we know what L of E2 is, we know what L of this guy is, so we just have to do some algebra to get what L of E3 is. So this implies that L of E3 is going to equal, well, L of 2 minus 1, 1 is 1, 1, 1, 1. And let's move over this expression here. So minus 2 times L of E1, which is 1, 2, 3, 4. And then we move over this expression and we get plus L of E2, so it's going to be 1, 0, 0, minus 1. So then all we have to do is a little bit of arithmetic. And what are we going to get? Alright, so we're going to get, this is a minus 2 here. Okay, so we're going to get a 0 there. And then we're going to get 1 minus 4, which is a minus 3. And then we're going to get a 1 minus 6, which is going to be a minus 5. And then we're going to get a 1 minus 8 minus 1. So this turns out to be just minus 8. So that gives us our answer to this third part D. The next question is just a bunch of true and false. So we have a linear transformation here going from Rm to Rn. Now notice that this is different from our usual order. Usually we put Rn here and Rm here, but we've swapped the order of the domain and the codomain. So our first question says that if n equals m, then L is 1 to 1. Is this true or false? Well, n equals m, that means that the matrix associated to L is square, and not all square matrices are 1 to 1. For example, I can give you the matrix like this, 0 matrix, he's square, and He is not one-to-one because the rank of this thing is not equal to its number of columns. Its rank is 0. Okay, so this guy here is false. So if L is 1-to-1, then n is less than or equal to m. Well, okay, so n is going to be in the matrix associated to L. N for us is going to be the number of rows, and m is going to be the number of columns. So what we're saying is it possible to have more rows than columns and still have L be 1-to-1? Well, yeah. Let me give you an example. Okay. So here is a matrix with more rows than we have columns, and it's 1-to-1 because its rank is equal to its number of columns. So this guy here is also false. Okay, so if m is less than or equal to n, then L is not invertible. Oh, this guy is true because if m is less than or equal to is less than n, strictly less than n, then it's not equal to n. In order to be invertible, we have to have the matrix associated L being square. So this guy here is true. Now, if L is on 2, then m is less than or equal to n. Now, this is saying that is it possible to have more columns than rows and have L be on 2? Well, this is, yeah, we can make an example like that. Okay, here we have more columns than we have rows, but this function is on 2 because its rank is equal to its number of rows. So this guy here is also false. And last, the kernel of L is a subspace of Rn. Now this is where we have to be careful and just look, oh yeah, right, the kernel of linear transformation is a subspace of the domain. The domain for us is Rm, not Rn, so this guy is also false. Alright, well that's it for question number 6 on the midterm. If you have any questions, you can ask me in class or in the comments below. Thank you very much.